Number 14. The Diver Cemetery. It looks harmless. The deadliest places in the ocean are supposed to advertise themselves with black water, crushing storms, or predators. Dahab's Blue Hole does the opposite. It is clear, calm, beautiful, and famous enough to pull in skilled divers from around the world. Yet beside this postcard shoreline stands a cemetery of memorial plaques. One of the most lethal traps in the sea is built from false clarity. That contradiction centers on the Arch, a roughly 26-meter passage that begins around 52 to 56 meters down. It looks like an exit. At that depth, the mind can start to slip just when precision matters most. In 2000, Yuri Lipsky descended here alone with a camera. The recovered footage turned an abstract risk into visible panic. We will keep that standard to the end. Among all the ocean's terrifying places, which one is worst in terms of what it can physically do? The postcard that learned how to kill divers. On April 28, 2000, a 22-year-old Russian-Israeli diving instructor named Yuri Lipsky entered the Blue Hole on Egypt's Sinai coast, about 10 kilometers north of Dahab in the Gulf of Aqaba. He carried a video camera. He went in alone. The water looks almost offensively inviting. Sunlight drops straight through it. The reef opens into a near-perfect bowl about 100 meters deep. In that blue water, a darker opening cuts through the wall, an underwater doorway leading to the open Red Sea. That doorway made the site infamous, but not in the simple way people imagine. The Blue Hole itself is a sinkhole in shallow coastal reef. Swimmers can see it from shore. Divers can enter from a beach. The approach feels manageable. And the second shape appears inside the first, the Arch, a tunnel-like passage through the reef, commonly placed around 50 to 56 meters below the surface and about 26 meters long. Close enough to see, deep enough to punish anyone who reaches for it on ordinary air. Lipsky kept descending. The recovered footage is hard to watch because nothing in it looks dramatic at first. No storm, no collapsing wreck, no attacking animal. Just clear water, a wall dropping away, and the slow loss of normal depth cues. In murky water, a diver gets warnings. Darkness thickens. Visibility closes in. The body understands it is leaving the safe zone. Here the Red Sea does something more dangerous. It stays blue. It stays open. It lets depth feel abstract until it suddenly is not. You hang in water so clear it barely seems real. The reef is beside you, then below you, then suddenly useless. Your bubbles sprint upward. You do not. Your instruments matter more than your eyes now, but your eyes keep telling your brain there is still time. At around 115 meters, Lipsky hit the bottom. That number matters. Ordinary compressed air becomes a different substance at that depth. Nitrogen can narcotize. Oxygen can turn toxic. Small buoyancy errors become vertical accidents. Panic burns gas faster. Gas at that depth disappears with shocking speed because every breath is taken under far greater pressure than at the surface. A diver is not dealing with one problem there. Several failures arrive together. Recovery diver Tariq Omar later brought up Lipsky's body and his camera. That camera is why this death became the one almost everyone knows. It did not explain the site with diagrams or training tables. It showed the human version, labored movement, disorientation, a desperate attempt to fix a situation that already had too many bad variables stacked inside it. For many divers, that footage changed Dahab from a famous challenge into a warning written in real time. The body count is strangely blurry. Some published accounts repeat roughly 130 deaths between 1997 and 2012. Others push the total above 200. There is no single clean public registry separating confirmed fatalities from rumor, duplication, and the mythology that grows around a place with this reputation. That uncertainty does not make the site gentler. It sharpens the feeling on shore. Names fixed into rock, dates, languages from different countries. A beach dive site becoming something like a roadside shrine. This is why the Blue Hole works as an opening measure for the whole question. It is terrifying on a human scale. Not because it is the deepest place in the ocean. Not because it can crush a steel hull or erase a sonar return. It can take a trained person in daylight, in warm water, within sight of shore, and make his judgment fail before the danger even looks like danger. The Arch drives that contradiction. Divers can see the possibility of an exit to open sea. They know it is there. Many come because it is there. But by the time that opening matters, the dive has already entered a range where air planning turns unforgiving, narcosis can blur decisions, and a wrong line through the tunnel can turn a passage into a trap. The opening in the wall is real. So is the belief that you can still choose it cleanly. Below 50 meters, those two facts split fast. Time Yuri Lipsky reached the bottom at about 115 meters, the famous opening above him was no longer an escape route. It was only a dark shape in blue water. Number 13. The perfect circle. What kind of underwater hole contains cave decorations that should only exist in air? On December 2, 2018, a small submersible dropped into the Great Blue Hole at Lighthouse Reef Atoll, about 80 kilometers off mainland Belize. Inside were Fabien Cousteau, Richard Branson, and pilot Erica Bergman. They were revisiting a place Jacques Cousteau had helped turn into legend after bringing the Calypso there in 1971. From above, it barely looks threatening. A nearly perfect dark circle, roughly 305 meters across, cut into bright turquoise reef water like ink on the sea. It sits inside a UNESCO World Heritage Reef System. Aircraft, satellites, and tourist helicopters have photographed it so often that it almost stops looking real. But postcards crush the scale. They do not show the rim dropping away. They do not show the blue closing in. You slip below the surface, and at first it behaves like a famous dive site should. Clear water. Reef life around the edge. Sunlight pouring down in columns. Then the wall turns vertical. The ring of coral gives way to limestone. At around 33 meters, about 110 feet, the hole reveals its impossible detail. Stalactites hanging underwater, some more than 6 meters long. That is the first sign the usual story does not hold. People talk about the Great Blue Hole as a marine abyss, a circular wound in the reef, a mystery made by the sea. But the evidence is hanging right in front of you. Stalactites do not grow in open ocean. They grow in air-filled caves, one mineral drip at a time. So this place has a stranger history than the brochures usually admit. This circle used to be dry land. Long before tourists flew over Belize to photograph it, and long before Cousteau called it one of the world's great dive sites, sea level during the ice ages stood roughly 100 to 200 meters lower than it does now. The limestone platform here was exposed. Rainwater dissolved the rock. Caverns formed. Ceilings weakened. Passages widened. The Great Blue Hole was part of a karst cave system, not a marine shaft. The ceiling eventually collapsed, leaving a sinkhole. Only later did rising seas flood it. That matters because the fear here is not the same as the Dahab Blue Hole we just left behind. Dahab punishes human error in a narrow depth window. This place is calmer, wider, more scenic, and easier to misread. It does not pull you toward a tunnel. It pulls you in with symmetry. Somewhere in the middle of that descent, the place earns its title, the perfect circle. That perfection is part of the trap. From the air it looks clean. In brochures it looks open. Inside, the geometry starts to feel less like beauty and more like a drop shaft. About 123 meters deep, nearly 400 feet, with walls descending into darker, poorer water, it strips away the features that usually reassure you underwater. Fewer fish, less motion, less noise. By roughly 90 meters, the deeper layer is anoxic, a low or no oxygen zone where ordinary reef life largely disappears. No swarm of predators, no cinematic monster, just water gone still in the worst possible way. The evidence keeps beating the myth. People describe the Great Blue Hole as if depth alone explains the danger. Depth is only part of it. The more disturbing fact is stagnation. The lower water column is not an active blue cathedral full of life. Closer to a flooded chamber with chemistry ordinary marine communities do not use. In 2018, the expedition mapped the interior in 3D and found a bottom less romantic than the legend suggests. A relatively flat floor, and around the perimeter a talus ring, collapsed debris rising as much as 25 meters, the broken remains of an older cave architecture. This is not an endlessly narrowing throat into the earth. It is the drowned remnant of a roof fall. The strangest detail is still overhead. You are hanging in seawater, looking at stone icicles that only make sense in open air. Each one is a timestamp from a world that no longer exists. For them to form, this chamber had to be dry. For them to survive, the sea had to arrive later. For divers to see them now, the ocean had to preserve enough of the cave to leave the evidence suspended in place. That makes this site matter to the larger question running through the whole video. If the most terrifying place is measured not by folklore but by physical effect, the Great Blue Hole belongs in a different category. It does not need trench pressure or vent heat or a famous death toll fixed into cliffside plaques. It takes a landscape built for land, drowns it, poisons the deep water, and leaves the proof hanging in silence. The official image of the Great Blue Hole is simple: a famous Belizean sinkhole, beautiful from above, about 1,000 feet across and 400 feet deep. The reality is more precise and less friendly. It is an Ice Age cave the ocean swallowed after sea level rose, and those underwater stalactites are there for one reason only: they formed in air before the sea got in. Number 12. The vertical dark. The Blue Hole drops past comfort and into chemistry. 300.89 meters. In July 2016, that number turned a dark patch in the South China Sea into an international headline. By itself, the number almost misleads. A hole this deep is not simply harder to dive. It becomes a different kind of place. In March 2016, a small Chinese research team reached Yongla Atoll at 16.31 north, 111.46 east. The reef there can be too shallow above the coral for a large research vessel. So they came in smaller: a flat-bottomed platform, a cable, a VideoRay Pro 4 underwater robot with a depth sensor. From the surface, Dragon Hole looked simple enough. A blue-black circle cut into pale reef water, like somebody had pressed a thumb straight down through the lagoon. The first impression was a vertical well. Then the measurements kept going. 100 meters, 200, then past 300, to a reported 300.89 meters. On July 24, 2016, Sansha authorities officially named it the Sansha Yongla Blue Hole, and state media presented it as the deepest known marine blue hole at the time. Later reports from Mexico overtook that claim, with Tom Jaw Blue Hole measured deeper at 423.6 meters. Dragon Hole did not become less disturbing when it lost the title. The title was never the problem. Start with access. A recreational diver already works on a strict clock tens of meters down. A technical diver can push much farther, but every extra meter adds gas planning, decompression obligation, and failure points, with almost no room for improvisation. Put the floor at roughly 300 meters inside a reef cavity, and rescue stops being a meaningful promise. It becomes a transport problem, a chamber problem, a timing problem, then, very quickly, a recovery problem. Now add shape. Later 3D mapping, published in 2018, showed that Dragon Hole is not a perfect cylinder drilled cleanly into the earth. It leans. Its walls vary. The shaft is irregular, hidden inside the reef like a cave that lost interest in symmetry. Straight depth is one hazard. Uneven enclosed depth is another. You are not descending through open blue water with a clean route above you. You are moving into a structure. The structure changes the water. At the top, Dragon Hole is still connected to the familiar reef world: light, fish, circulation, oxygen. Below that, the numbers shift from geometry to chemistry. Studies describe a sharp transition beginning at roughly 90 to 100 meters. Oxygen falls away. Light fades with it. Sulfide begins to appear. The lower water mixes poorly with the open sea. The deep part of the hole behaves less like a shaft in the ocean and more like a chamber with its own rules. At that point, deep stops meaning distance. Picture the descent in layers. At 20 meters, the opening above is still broad and bright. At 50, the walls start to dominate your view. At 90, the water column is not just darker, it is less alive. Ordinary reef life thins out because the chemistry is changing under you. Go lower and the problem is no longer only pressure, or narcosis, or ascent profile. The water itself is becoming hostile to the kind of animals, and the kind of rescuer, that would normally share this space. The forensic detail is brutally simple. A ship can float over Dragon Hole and notice almost nothing. Coral water, calm surface. Neat, dark circle. But inside that circle, the environment is stacked vertically. Normal water above, oxygen-starved water below. The lower layers are so isolated that biology and emergency response both hit a wall at nearly the same depth. That makes the reported 300.89 meters matter more than it first appears. Not as an impressive statistic. At this scale, depth creates separation. Separation from sunlight, separation from easy ascent, separation from the surrounding sea itself. The hole stops behaving like an ordinary diving site and starts behaving like a contained system. In October 2016, authorities established a protection zone extending 1 nautical mile around the site and banned fishing and sightseeing there. That sounds like routine management. It says something more specific. Dragon Hole had already shifted categories. It was no longer just a curiosity in the reef. It was a monitored vertical environment with enough scientific value and enough hazard to keep casual traffic away. Even the famous image is wrong. The popular version shows a flawless ocean well, round and pure, an almost abstract hole in tropical water. The mapped version is messier, angled, uneven, chemically layered. Not an elegant shaft, but a concealed marine cave whose lower reaches are cut off from ordinary exchange. That first 300-meter headline was never really about whether a diver could go deep enough. It was about what depth was doing to the water once the sunlight stopped and circulation weakened. Dragon Hole answers with numbers, not legend. Below about 90 to 100 meters, oxygen collapses towards zero, sulfide appears, and the lower chamber turns into water that does not behave like the sea above it. Number 11. Lakes under the sea. In 2014, a NOAA remotely operated vehicle drifted over the Gulf seafloor, 1,260 meters down, and found a shoreline where no shoreline should exist. The camera passed over ripples and a sharp edge, as if a dark pond had collected in a hollow at the bottom of the ocean. Small waves shivered on its surface. Crabs picked along the margin. Fish crossed the boundary and slowed. Some never came back out. The lake where drowning happens underwater. South of Louisiana, on the northern slope of the Gulf of Mexico, the seafloor lies over buried salt older than the Gulf as we know it. Over time, that salt has been squeezed upward through younger sediments. Where that hidden geology leaks, it creates something that looks wrong at first glance. Water behaves as if it has found land. The result is a brine pool, a basin of hypersaline liquids so dense it settles into depressions instead of mixing cleanly with the seawater above. Measured by what a place can physically do, this one is frightening in a strange way. It does not crush like a trench. It does not burn like a vent. It rewrites one of the simplest rules you expect water to follow. Here, even drowning has another layer. The classic description came in 1987, when Ian MacDonald and colleagues described Brine Pool NR1 at about 650 meters depth. What they found was more than salty water. It was a seafloor pockmark holding brine with a salinity of 121.35 practical salinity units, far beyond normal seawater, and dissolved oxygen at or below 0.17 milliliters per liter. In plain terms, almost none. The pool was rich in methane, poor in oxygen, and chemically hostile enough to act like a trap. The rim was alive. Around the edge sat a ring of mussels later known as Bathymodiolus childressi. That can sound almost decorative until you look at what the animals are actually doing. They are not grazing on sunlight-fed particles drifting down from the surface. They live exactly where two bad environments meet and create one survivable one. Their bacterial partners consume methane rising from below, but they also need oxygen from the seawater above. So the mussels cluster at the boundary itself, right on the invisible beach. The longer you look, the worse it feels. The lethal zone is also a feeding zone. Death sits a few centimeters from a perfectly good living. A fish slips too low and enters water that can suffocate it. A crab wanders over the line and stalls out. On that same line, life has built an economy. Later dives made the scene stranger. During NOAA's 23-day Gulf of Mexico expedition in 2014, explorers documented a large brine pool bordered by carbonate formations that looked like pale islands around a black inland sea. Popular coverage gave one such place the nickname Jacuzzi of Despair. It sounds a little silly until you see methane bubbles rising through the brine like a simmer. In some Gulf pools, methane concentrations have been measured up to 33 millimolar inside the brine itself, while the water directly above can hold concentrations 3 orders of magnitude lower. A few feet apart, same basin, radically different chemistry. The camera sees a surface that is not really a surface, yet animals treat it like one. A crab stands at the edge. A fish crosses it. Vehicle's lights catch a wavering line, and your brain reads it as shore because, in every useful visual sense, it is. Below that line is denser, saltier, oxygen-poor liquid loaded with seep chemistry. Above it is ordinary seawater by comparison. The border is not imaginary, it just is not made of rock. Here the horror slows down. It is not violent, it is not sudden, it is clinical. An animal entering the pool is not attacked. There are no teeth, no impact, no dramatic struggle in the usual sense. It passes from one fluid into another that its body is not built to handle. Oxygen drops away. The chemistry turns wrong. Movement slows. If it cannot leave quickly, it dies in a place that looks, impossibly, like more water. In this pocket of the ocean, still afloat can mean already dying. Few places in the sea let the environment imitate safety this well. A trench announces depth. A vent announces heat. A storm announces force. A brine pool looks contained, smooth, almost calm. A quiet basin, a level surface, a dark mirror on the bottom. Cross that boundary unprepared, and it can do real physiological damage. Scientists still do not fully know how stable individual Gulf brine pools remain across decades. Their outlines are shaped by seepage, salt, methane, slope processes, maybe even hydrate changes. The shoreline may not be fixed in any human sense. It may creep, pulse, or redraw itself over time. A lethal lake on the seafloor does not need waves or weather to change. It only needs the geology beneath it to keep breathing. That explains the image that seemed impossible at the start. Those waves at the bottom of the sea are real enough to film because the brine is much denser than the seawater above it. The two layers resist mixing, so the heavy brine settles into hollows and holds a visible boundary like a hidden shoreline. Not land, not illusion. A separate body of water resting inside another one. Total silence. Then something slips over the edge. Number 10. White Towers. In Search of Hydrothermal Lost Cities. That was the title on the expedition material in December 2000. At the start, it sounded less like a destination than a dare. Deborah Kelly, Gretchen Frew Green, Jeffrey Carson, and the rest of the National Science Foundation team were working the Atlantis Massif, a block of exposed mantle rock just west of the Mid-Atlantic Ridge near 30 degrees north. They were there to understand how that mountain formed. Then the seafloor images came back. Roughly 15 kilometers off the active spreading axis, at about 750 to 900 meters down, the cameras showed none of the familiar script of a vent field. That distance mattered immediately. Most hydrothermal systems cluster where fresh magma and fractured crust make the heat source obvious. 15 kilometers away, the usual map of where a vent should be was already failing. No black smoke boiling upward. No dark metal chimneys around a ridge crest. The lights caught pale columns rising from the bottom instead, white and cream against the blue-black water. They had ledges and spires and broken crowns, like a drowned city seen through dust. Some were venting, and what came out did not look explosive. It looked patient. The place feels wrong for a different reason. You descend expecting violence, because that is how most frightening places in the ocean first announce themselves. Impact, heat, depth, pressure. Here the first impression is architecture. Limestone-colored towers, quiet walls, openings breathing into the dark. The tallest structure, later named Poseidon, stood about 60 meters high, the height of a 20-story building, built where no city should exist at all. Documents get stranger the closer you read. The site sat on crust around 1.5 million years old enough to undermine the easy assumption that vigorous venting must fade with youthful volcanism. If chemistry can keep a system alive on crust like that, then hydrothermal activity does not vanish as neatly as some models want it to. The fluids were not the blistering kind that define black smokers. They ran roughly 40 to 91 degrees Celsius, cooler than the famous superheated vents, but in one sense more provocative, because those temperatures are gentle enough to preserve and drive complex organic reactions instead of simply burning through them. Their pH reached about 9 to 11, strongly alkaline, reversing the acidic intuition many viewers bring from other vent systems. That matters because the gradient between alkaline vent fluid and more acidic seawater can act like a natural battery. Everything about it said vent field. Almost nothing about it matched the usual power source, chemistry, or location. So the name stuck because nothing else fit better. Lost City. At first, not poetry so much as field description. A cluster of carbonate chimneys and pinnacles that looked less like industrial geology than abandoned construction. White towers, terraces, flanges, brittle-looking surfaces. A city-shaped consequence of reactions deep inside the seafloor. Its threat is not the immediate kind. Lost City does not rise in the mind because it can shred a submersible or boil a diver in seconds. It matters because it makes the deep Atlantic behave like a long-running engine for life-supporting chemistry in total darkness. That widens the scale of the problem. Trench tests what a body can survive. This site tests what a planet can do with rock, water, carbon, and time. Inside the chimneys, microbes live in pores and cracks where alkaline fluids move through carbonate walls. They do not need daylight. They feed on chemical disequilibrium, hydrogen, methane, mineral gradients. This is a place where the ocean and Earth's interior meet directly, and the result is a habitable micro-world hidden inside stone. The fear here lands differently. What if this is one of the settings that taught matter how to become biology? If that is even partly true, then these towers are not just an origin story with good visuals. They are evidence that the ingredients for metabolism-like systems may emerge wherever water works through mantle rock long enough. And if that chemistry is common, the consequence cuts in two directions at once. Life may be easier to start than we hoped, or our old confidence about where to look for it may be badly misplaced. By this point, the image keeps defeating instinct. White usually reads as cold, limestone usually reads as dead, ruins usually read as aftermath. These towers are active. They grow, fracture, seal, reopen. Carbonate and brucite accumulate into walls that redirect flow, shut one passage, open another, and rebuild the silhouette of the field over time. The field does not simply sit there glowing in the dark. It rewrites its plumbing. Scientists still argue over how long the system has truly been active. Some dating places hydrothermal activity there at least tens of thousands of years back. Other work suggests it may have persisted much longer. That uncertainty is not a bookkeeping detail. The system that can endure on these timescales offers an enormous window for chemistry to repeat itself, stabilize, and select for whatever survives inside the pores. Long activity also creates a harder question for Earth history. If places like this were more common on the early planet, how many beginnings did life get? That returns you to the first image in the expedition record. The team did not arrive to confirm a legend. They were surveying mantle rock. Then the cameras crossed a patch of deep Atlantic where the known categories stopped fitting. White chimneys stood in the dark, as if the seafloor had switched materials and decided to build in bone. They looked wrong for a reason. These were not ordinary smokers driven mainly by fresh magma at the ridge axis. The towers existed because seawater had penetrated mantle rock and reacted with it. Peridotite changed. Hydrogen formed. Methane-bearing alkaline fluids rose back out. That explains the mechanism, but it does not close the case. It opens a larger one. If rock this old and this far off axis can keep manufacturing chemical fuel, then Lost City is not a beautiful exception. It is a warning that habitable environments may persist where our models least expect them, and that the line between barren stone and living chemistry may depend on processes we still do not know how to count. Number 9. Black smoke. In 1997, on a French-led expedition along the Mid-Atlantic Ridge, researchers came down on a site near 36 degrees 14 minutes north and found that the dark was already busy. About 2,300 meters below the Atlantic, where the water sits only a few degrees above freezing, the seafloor was throwing up black clouds like an engine room on fire. Chimneys stood in clusters. Fluid blasted out of them at around 365 degrees Celsius. At the surface, that heat would flash violently into steam. Down here, it did not boil. Here, Rainbow stops resembling the gentle cousin of Lost City and starts looking like something built for the wrong planet. Lost City was pale, alkaline, almost ghostly. Rainbow is black, acidic, metallic. The water coming out has a pH around 2.8, not seawater, closer to a chemical burn. In a video asking which place is most terrifying when you measure what it can physically do, Rainbow earns its place in a strange way. It is not just the depth. It is the chemistry being remade around you. Picture it at the bottom of the ocean, in total darkness, beside a furnace no human hand lit. The rock under you is not ordinary basalt. Rainbow sits on ultramafic mantle rock, exposed peridotite, material from deeper in the earth than vent fields usually reveal. Seawater seeps down through cracks and meets hot rock. The rock changes, and the water changes with it. Geologists call that serpentinization. In plain English, the seafloor is chemically eating itself. The vent is not only hot, it is productive. It manufactures fuel. Studies of rainbow's fluids found hydrogen concentrations around 16 millimoles per kilogram and methane around 2.5. Numbers sound small until you place them in a world with no sunlight. Hydrogen is energy. Methane is energy. Dissolved metals ride with them in the plume. Acid comes with them. Heat comes with them. This is a natural reactor under thousands of tons of overlying water, feeding microbes and vent animals from chemistry alone. The deep ocean is not empty. Here it looks industrial. The longer you stare at it, the harsher it gets. Black smokers are often described as oases. That is true from the point of view of the animals clinging to them. It is less true if you think like a body, a hull, or an instrument package. The chimneys are brittle towers built from precipitated minerals. The plume is loaded with metal-rich particles. The surrounding seawater is near freezing. The vent fluid punching through it is hundreds of degrees hotter. The gradients are savage. A few meters can separate water that is merely dark and cold from water that is acidic, opaque, and hot enough to wreck assumptions. That is what makes Rainbow more terrifying than its postcard version. It is not a hidden garden. It is a collision zone between extremes: cold and superheated, seawater and mantle rock, biology and geochemistry. One detail makes it stranger still. Rainbow and Lost City are cousins only in the loosest sense. Both are tied to serpentinization, but Lost City releases cooler alkaline fluids. Rainbow takes that same deep rock-water reaction and plugs it into a high-temperature black smoker system. Same family, very different mood. If you were hovering there in a submersible, lights fixed on those chimneys, the first thing you would notice would not be beauty. It would be violence without motion you can feel. The Atlantic above is still. The vent field below is all conversion. Rock to altered rock. Seawater to acid fluid. Chemical energy to living tissue. Invisible reactions, visible smoke. Researchers still argue over one part of it. How much of Rainbow's methane is being made abiotically, directly by rock-water reactions, and how much is being altered, consumed, or recycled by microbes before it escapes into the plume? That uncertainty matters because Rainbow sits on a fault line in our ideas. If a place can generate hydrogen and methane this efficiently without sunlight, deep ocean chemistry stops looking like background scenery. It starts looking like an engine, one that can blur the border between geology and the ingredients life knows how to use. In a ranking of terrifying places, that is a different kind of threat, not just to a human body, but to any neat theory that says life needs the familiar surface world first. So come back to the first paradox. Water at 365 degrees Celsius should be steam. It should roar out as vapor. It should not remain liquid in black jets 2 1/3 kilometers under the Atlantic. But Rainbow sits beneath such immense pressure that the ordinary boiling point no longer rules the scene. The water column above it is heavy enough to keep that superheated fluid from flashing into gas. Pressure changes the rules. At about 2,300 meters down, the furnace cannot boil. Number 8. The Sea Without Shores. On October 4, 1492, Christopher Columbus was crossing the North Atlantic when his sailors saw the ocean change. Brown weeds spread across the surface in long, drifting rafts. The water turned strangely calm. The wind weakened. In the ship's log, the weed was described as looking like rocks in the sea. For men already deep in an unknown ocean, that detail mattered. Rocks meant shoals. Shoals meant land, or wreckage. There was no coast ahead, no beach anywhere around them. Only open Atlantic, flat blue water, and vegetation floating where a sea should have been empty. How can a sea exist if it has no shores at all? A sea with no coast to escape toward. The first stories made it into a graveyard. Weed-choked water, stalled ships, crews staring at a horizon that never changed. Later, the same region was absorbed into Bermuda Triangle lore, vanishings, and derelict ship tails. The image is easy to believe because the sensory details do the work themselves. Broad mats of brown weed, weak winds, too much stillness, no land anywhere to measure yourself against, and just enough floating clutter to suggest that something has already gone wrong here. What matters is not a supernatural curse. It is a real piece of ocean with a behavior that can mislead you. The Sargasso Sea covers roughly 4.16 million square kilometers in the North Atlantic, with a shifting core often placed between 22 and 38 degrees north and 76 to 43 degrees west. Those numbers sound clinical until you imagine trying to cross them under sail. Unlike every other sea you can name, this one is not bounded by land. NOAA defines it by motion, by the circulating currents of the North Atlantic subtropical gyre. Its edges are not something a captain can see. The Gulf Stream on the west, the North Atlantic Current to the north, the Canary Current to the east, and the North Atlantic Equatorial Current to the south create a rotating enclosure made of moving water. That means your boundary markers drift. A chart cannot show you a shoreline to aim for. A weak patch of wind, a thickening field of weed, a compass heading that should feel decisive but does not. These become your only clues that you have entered a place designed less like a bay than a trap that redraws itself. Cross into it in a wooden sailing ship, and the distinction between open ocean and enclosed sea becomes survival. The winds can slacken, the horizon stays empty, the weed keeps appearing. Every hour you fail to make progress is an hour of fresh water lost, food spoiled, crew morale fraying, and navigation becoming less certain. In the age of canvas, danger was not always impact. Delay could kill just as efficiently. A calm zone that holds you in place can turn a routine crossing into disease, rationing, mutiny, or a drift into storm tracks you had tried to avoid. That is how the legends took hold. Sailors did not need a solid mat they could walk on. They needed a place that could keep them from leaving quickly, while surrounding them with false signs of land and wreckage. The modern correction matters, but it sharpens the fear rather than removing it. NOAA has spent years pushing back against the image of a literal floating continent of trash in the North Atlantic garbage patch system. The debris in gyres is dispersed. Dispersed does not mean absent, and it does not mean safe. A retention zone does not have to pile everything into one visible island to change what the sea carries, hides, or delays. The Sargasso Sea collects. It collects the two floating seaweeds most associated with it, Sargassum natans and Sargassum fluitans, rafts of life with no roots to any seabed. It collects young sea turtles, which shelter beneath the weed in the open ocean. It collects larvae and juveniles. It collects debris. It also collects confusion. A mat of sargassum can look like a stable feature when it is not, a navigational hint when it is only drift. Plastic fragments mixed into the weed do not announce themselves from a deck or cockpit. They move through the same retention system as living nursery habitat. The same circulation that protects fragile life can also concentrate hazards small enough to ignore until they accumulate into damage. This is one of the few terrifying places in the ocean where the threat is not pressure, heat, or depth. It is retention. A trench crushes. A vent field scalds chemistry into visibility. The Sargasso Sea holds on. That changes the stakes in a modern ocean. Retention can concentrate plastics, tar, fishing gear, toxins riding on fragments, and weak signals from vessels or aircraft into the same broad, shifting field. It can delay search efforts by making debris look natural, and natural cover look like debris. It can keep evidence circulating just long enough to separate cause from effect, so that by the time something is found, it may no longer point cleanly back to where trouble began. That is where the legend survives, not in monsters, but in misreading. Tropical Atlantic sargassum blooms that foul Caribbean beaches are often confused with the classic Sargasso Sea ecosystem because the name is the same. The biology and geography are more complicated than that, and the mistake matters. If you collapse all brown weed into one story, you miss what frightened sailors in the first place. It was not simply seaweed. It was seaweed appearing far from land, in a place with no visible limits, and lingering because the water itself kept rebuilding the enclosure. Then there are the eels. For more than a century, the Sargasso Sea has carried another reputation, quieter and stranger than ghost ships. European eels and American eels are understood to spawn there. They leave rivers and coasts and ocean away and return to this broad Atlantic region to begin the next generation in water humans still struggle to witness directly. Scientists have tracked migrations and narrowed the geography, yet the exact spawning act in the wild has remained extraordinarily elusive. In a sea defined by moving boundaries, even one of the best-known migrations on Earth ends in a place we can enter without fully seeing what happens inside it. So the region famous for vanishings does not need fantasy to feel wrong. It offers calm water that looked threatening in 1492, floating weed that resembles evidence of land where there is none, debris gathered without forming a clear target, and animals returning to reproduce in a zone we can map but still fail to watch at its most important moment. Officially, it is a region of the North Atlantic bounded by currents rather than coasts. In practice, that means the border is always moving, and anything caught there can be carried, concealed, delayed, or mistaken without anyone realizing when it crossed in. Number 7. The Pattern Machine. FT. On December 5, 1945, that call sign started dissolving into static over the western North Atlantic. At 14:10 local time, 5 U.S. Navy TBM Avenger torpedo bombers lifted off from Naval Air Station Fort Lauderdale for a routine navigation exercise. 5 aircraft, 14 men. A training flight over water that should have ended before dinner. It did not. Radio traffic turned confused. Headings no longer matched the map. Somewhere east of Florida, the Atlantic took away the one thing that keeps fear under control: a fixed location. Lieutenant Charles C. Taylor, the flight leader, was experienced. Over open water, experience depends on something brutally simple. You have to know what you are looking at: a flat horizon, scattered islands, weather that shifts, fuel dropping minute by minute. In that kind of space, a small mistake does not stay small. Taylor became convinced his compasses were failing, and that the flight was over the Florida Keys, not the Bahamas. That sounds technical. It was more dangerous than technical. If he was right, the correct move was one direction. If he was wrong, that same move pushed 5 aircraft farther into the Atlantic. The whole moment narrows to a document and a voice. Radio operators copying fragments, pilots answering without confidence, ground stations trying to triangulate signals that would not settle into a clean point on a chart. One of the other aviators doubted Taylor's position. Others sounded lost with him. Dusk came down. Weather worsened. Fuel kept burning. The problem turned into arithmetic. This is the case people reach for when they want proof of the Bermuda Triangle. Flight 19, the patrol that vanished and left almost nothing behind. But the immediate danger was never a legend. It was a navigational error widening in real time, while every recovery option got worse. Once the track blurred, the risk spread outward, from the cockpit to every ship and aircraft that would have to guess where to look. When Navy stations lost confidence in Flight 19's exact position, the event changed shape. It was no longer only 5 planes trying to get home. It became a search problem over darkening water with no reliable center, no impact site to inspect, no burned field, no wing in a tree. Only a widening radius and less light to work with. And the search was enormous. More than 200,000 square miles across the Atlantic and Gulf of Mexico. One of the largest air and sea searches of its time. Ships, aircraft, radio stations, charts, estimates, revisions. The scale sounds powerful until you picture what it means operationally. Every bad coordinate wastes fuel. Every wrong assumption pulls rescuers into the wrong box. In open water, search geometry becomes its own hazard. Then the story deepened. A PBM-5 Mariner search plane, Bureau number 59225, launched to look for the missing Avengers and vanished that same evening. The practical danger sharpened instantly. A rescue mission had become another loss to plot, another crew to account for, another patch of ocean competing for attention. The Mariner had a reputation among some crews as a gas tank, vulnerable to fuel vapor explosion. That likely explanation did not reduce the damage. It made the situation worse in a different way. If search aircraft can disappear before confirming anything, then the act of investigating starts generating fresh uncertainty. That is where these waters become more than a backdrop. They are heavily traveled. Weather shifts fast. The Gulf Stream can scatter floating debris and push it far from the point of impact, So the first object found may mislead as easily as it helps. The seafloor drops into deep zones where wreckage can vanish from reach. A crash on land leaves a scene. A crash at sea can erase the scene before sunrise. The famous triangle shape, Florida, Bermuda, Puerto Rico, feels official because it is familiar. It is not an official NOAA danger zone outlined on some master government chart. The name came later, popularized in 1964 by writer Vincent Gaddis in Argosy magazine. But that fact matters here for a reason beyond trivia. Once a broad cultural outline existed, unrelated losses could be pulled into the same frame, and that made future incidents harder to read clearly. A map shape became a sorting machine. It did not solve disappearances, it blended them. NOAA's clarification about compasses points to the same practical problem. In some parts of the region, a compass may indicate true north rather than magnetic north. If a navigator mishandles that difference, the result is not magic. It is drift, misidentification, and a position error that grows with time. Out over water, that error does more than endanger one crew. It contaminates the record everyone else depends on afterward. The Bermuda Triangle spread so easily through popular culture because it could gather older losses and make them feel connected. March 1918, USS Cyclops disappeared with 306 crew and passengers, still the largest non-combat loss of life in U.S. Navy history. For investigators, the crucial fact was not atmosphere, but absence. No final wreck to inspect meant no decisive ending to anchor the case. For later navigators and rescuers, that kind of unresolved history has consequences. It teaches the wrong lessons as easily as the right ones. It turns caution into folklore and evidence into argument. That is what makes this stretch of ocean dangerous in a way that keeps compounding. It can turn men with instruments into voices arguing over where they are. It can turn a search into a moving mathematical problem. It can damage the record so badly that later crews inherit stories where they needed usable conclusions. For Flight 19, the central uncertainty never went away. Why did Taylor become so convinced he was over the Keys, instead of east of Florida near the Bahamas? Despite radio evidence and the doubts of other pilots? Without wreckage, the final track remained unresolved. And unresolved cases do not stay still. They alter charts in the mind. They distort search expectations. They invite the next emergency to begin with bad comparisons and missing proof. Out here, the most dangerous consequence may come after the disappearance. The same water that takes the aircraft can take the evidence. And when the next distress call comes in, who is navigating by facts, and who is navigating by a legend? Number 6. The Atlantic Scar. Of Puerto Rico, the seafloor drops into darkness while the island's busiest coasts stay exposed in full daylight. Ports, roads, hotels, neighborhoods, and beaches packed close to the water because there is little room to build anywhere else. When that offshore system shifts, the problem is not only what happens in the deep, it is how fast danger can cross the short distance to shore. The depth sharpens that threat. In the Puerto Rico Trench system, the Milwaukee or Brownson Deep reaches 8,750.8 meters. But the more unsettling fact is proximity. This abyss is not a remote curiosity in the middle of an empty ocean. It sits beside inhabited islands, and the structures linked to it can affect people who may only get minutes to react. That is where the geology stops being a reference card and becomes a coastal problem. The boundary north of Puerto Rico is not a single clean fracture with one obvious behavior. One part bends downward. Another part slips sideways. NOAA emphasizes mostly lateral motion with a smaller subduction component. USGS identifies Puerto Rico and the Virgin Islands as especially exposed to large earthquakes and tsunamis. For anyone on shore, that means the first clue may be ambiguous. A strong quake does not point to only one outcome. It can damage buildings, cut power, block roads, and still leave open the question of whether the sea is about to move next. Now picture the seafloor itself. Long east-west faults, strike-slip motion, subduction-related structure. Large submarine landslide scars cut into the slope. Those details matter because each one suggests a different way a bad morning begins. Rupture can shake homes and crack seawalls. One displaced block can jerk the seabed enough to disturb the water above it. One collapsing scar can send a wave toward shore without giving people a simple, familiar script to follow. Tsunamis do not require one perfect mechanism. They only need enough seafloor or enough unstable sediment to move in the wrong place at the wrong second. On the morning of October 11, 1918, that sequence reached land. A major earthquake struck near the Mona Passage, west of Puerto Rico. In Mayagüez and Aguadilla, buildings were damaged by the shaking. Then the shoreline changed. Contemporary reports, later compiled by U.S. scientists, described the sea withdrawing and then returning as a tsunami. People who had already survived the quake were caught by water minutes later. The 1918 event remains the greatest tsunami recorded in Puerto Rico. The escalation after 1918 is not just that the region stayed hazardous, it is that the lesson was incomplete. Scientists still debate how much of this margin is locked, how stress is distributed, and which failure mode is most likely in a given event. That uncertainty is its own danger. If the source mechanism is not obvious, warning decisions get harder. A shaking event may be followed by a tsunami, or by none, or by one generated through a pathway that reveals itself late. Evacuation cannot wait for perfect diagnosis, yet false certainty can waste minutes people do not have. The forensic picture grows stranger beneath the islands. Earthquakes under Puerto Rico and the Virgin Islands extend to depths greater than 150 kilometers. So the hazard is not confined to a narrow line on a map. It occupies a vertical column of rock, with stress released at different depths and in different styles. For a resident, that complexity translates into a brutal, practical question. After the shaking starts, what exactly have you just felt? A shallow rupture near the coast? A deeper event with less tsunami potential? A trigger for slope failure offshore? The ground does not hand out labels. That is why this margin is harder to read than places with a simpler script. In some regions, the mechanism is clearer and the expected sequence is easier to teach. Here, several pathways overlap. Tectonic rupture, seafloor displacement, gravitational collapse, and combinations still argued over in the literature. The challenge is not merely scientific classification, it is recognition under pressure. Emergency managers, sensors, and coastal residents all have to make decisions before the boundary has fully explained itself. In December 2018, Victor Vescovo took DSV limiting factor into that Atlantic abyss. The descent did not create the story, it clarified the setting. What looks like a statistic on a chart is part of an active trench system directly connected to inhabited coasts with a real earthquake and tsunami history. From a pressure sphere in the dark, you can trace a line to a waterfront street in Puerto Rico. The line is short enough that offshore complexity becomes onshore consequence. Look at the map and the shape stays unnerving. The trench runs like a crease along the northern edge of the islands. North of San Juan, the seafloor falls into hadal darkness. South of that drop are millions of people spread across Puerto Rico and nearby islands, with major development concentrated near the coast because island geography leaves little alternative. The deep does not remain politely offshore. It helps define what the margin can do during failure, and how little time shorelines may have to understand it. The most frightening number here may not be 8,750.8. It may be minutes. Minutes between shaking and water. Minutes in 1918 between the earthquake near Mona Passage and the tsunami that followed. Minutes in which a family checks a damaged house, a driver turns back toward a flooded road, a hotel worker hesitates over whether to clear a beach, and the second threat is already moving. By the time the sea pulled back along Puerto Rico's west coast in 1918, the offshore system had not become simpler or more readable. It had only proved that the next danger can arrive before people recognize which kind of event they are in. The unresolved threat is not just the force itself. It is whether the next minutes will be understood in time. Number 5. Deepest Atlantic Point. On December 19, 2018, Victor Vescovo sat inside a titanium sphere no wider than a small room and began dropping into the Atlantic north of Puerto Rico. Above him was the support ship DSSV pressure drop. Below him was a place called Milwaukee. Not a city, not a harbor. A point on the seafloor more than 27,000 feet down, known for decades on charts, but still waiting for a human being to reach its verified bottom. The Atlantic's lowest confirmed point. The name feels misplaced. Milwaukee sounds flat, inland, continental. Here it marked hadal darkness at the edge of the Caribbean. Vescovo's dive gave that label a physical reality. The submersible was DSV limiting factor. The mission was the opening Atlantic descent of the 5 Deeps expedition. The target was Milwaukee Deep, the low point inside the Puerto Rico Trench. One man, one pressure sphere, one descent to the deepest Atlantic location a modern expedition was prepared to verify in person. At the surface, the ocean looks ordinary. Trade wind water, shipping lanes, an island arc with beaches, ports, apartment towers, and airport runways. But 75 to 80 miles north of Puerto Rico, the seafloor buckles into something else. The trench runs roughly 400 miles east to west. In places, it is more than 20 kilometers wide. Where the North American plate meets the Caribbean plate, the bottom drops past 8 kilometers into a tectonic scar that sits startlingly close to so many people. The threat here is not folklore. It is shape and distance. You can leave San Juan by boat in daylight and head toward a place deep enough to crush steel, dark enough to erase noon, and unstable enough that NOAA expeditions in 2002 and 2003 mapped a major fault system there, the Bunce Fault. The trench was not just a bathymetric curiosity, it was an active structure with consequences. As limiting factor sank, the bright upper Atlantic faded to blue, then to Hadal black. First come the layers fish still use, then the layers where almost nothing large moves, then the depth where the ocean stops feeling like water and starts feeling like weight. At about 8,376 meters, by the expedition's figure, every square inch of the hull was carrying a load beyond normal intuition. Outside, pressure hit every surface at once. Inside, one pilot sat with instruments, lights, and the thin comfort of engineering done correctly. This was the first manned dive of the expedition and the first solo human descent to the deepest confirmed point in the Atlantic. That distinction matters. The Puerto Rico Trench had already been sounded, argued over, and redrawn for generations. Older references sometimes put the maximum near 8,740 or 8,750 meters. NOAA often describes the trench as exceeding 8,400 meters. 5 Deeps reported a verified dive depth of 8,376 meters. Same abyss, different numbers. In deep ocean work, that gap is not trivia. It marks the line between a place inferred from echoes and a place fixed by modern multi-beam sonar, navigational control, and a person reaching the bottom. The descent was doing 2 jobs at once. It was testing a machine. It was also testing a claim. This the Atlantic's deepest point? And if it is, which depth survives better instruments? The older ocean was filled with named depths, inherited from single-beam soundings and long stretches of inference. The modern ocean is less romantic and more disturbing. It trades myth for evidence. The evidence says this trench is not merely deep, it is measurable, active, and near. Near enough that the island shelf behind Vescovo was not an abstraction. Near enough that tectonics here matter to real coastlines. The Puerto Rico Trench sits beside one of the most striking gravity anomalies on Earth, where the crust is pulled down with unusual severity near the Puerto Rico Virgin Islands block. Faulting enters the picture. Steep relief enters the picture. Submarine landslides enter the picture. Tsunami modeling does too. The deepest Atlantic point stops being a remote dot for specialists. It becomes part of the physical system above which people build roads, ports, schools, and waterfront neighborhoods. That is what sharpens here. What can a place physically do? Milwaukee Deep can force modern science to keep revising the map. It can sit beside populated islands as part of an earthquake-capable plate boundary. It can carry a name taken from a warship and hide that history so completely that, to most people, the word sounds almost harmless. At bottom, Vescovo completed the Atlantic objective and gave the trench its clearest human witness so far. The dive did not settle every argument over measurement, but it narrowed the range. This was no rumor on a chart, no legendary hole. It was a surveyed target reached by a manned submersible on a dated expedition, with a reported bottom time and a reported depth. That is how an abyss becomes harder to ignore. And Milwaukee? The name goes back to the USS Milwaukee, tied to early sounding work in the region when naval surveying first turned this unseen low point into something mappable enough to label. The warship's name stayed. The number beneath it kept changing. In 2018, the label finally got a human visitor. 8,376 meters. December 19, 2018. First solo dive to the deepest verified point in the Atlantic. Number 4. The giant amphipods. On May 10, 2014, in the southwest Pacific north of New Zealand, a vehicle named Nereus was working almost 9,990 meters down when its voice vanished. One moment, the Woods Hole team was reading telemetry from a machine built for exactly this job. Full ocean depth, hadal exploration. The places ordinary submersibles do not reach. Then contact broke. Hours later, bits of debris floated up. Not a disabled robot. Not a recoverable failure. A machine built to survive the deepest trenches had most likely been crushed into fragments by nearly 1,000 atmospheres of pressure. By that depth, fear is no longer about what a person can see. It is about what the place does to the instruments sent ahead. Milwaukee Deep showed that even the map can be uncertain. The Kermadec Trench adds something harsher. Here, the measuring tool can be destroyed. The trench is commonly sighted at about 10,047 meters deep. It is part of the Tonga Kermadec system, stretched across one of the most active pieces of seafloor on Earth. This is the hadal zone, roughly 6,000 to 11,000 meters down. These trenches occupy less than 1% of the marine realm, but account for about 40% of the ocean's total depth range. The numbers feel abstract until you picture the place. No light, cold water, steep walls, a plate boundary where the Pacific Plate dives beneath the Australian Plate. The same geometry that opens the abyss here also loads earthquakes above it. And in that pressure, small things stop staying small. At first, the claim sounds backwards. Deep ocean trenches are supposed to be places of scarcity. Little food drifts down. Temperatures hover just above freezing. Pressure climbs to levels that flatten most hardware. You would expect creatures to be thin, slow, reduced to the minimum. But expeditions in and around the Kermadec documented deep-sea amphipods, including Alicella gigantea, a crustacean so oversized it sounds like someone scaled up beach life in the dark. Amphipods are relatives of the tiny shrimp-like scavengers that turn up by the thousands in cold marine environments. Usually they are background life, a few centimeters, easy to miss. But Alicella gigantea can reach lengths around 30 centimeters, roughly a foot. In a habitat defined by starvation, compression, and isolation, that size feels wrong. It is one of those hadal facts that lands a second late. The trench does not simply allow life there. It bends the limits enough that even the scavengers look exaggerated. Scale matters here because the Kermadec is not an empty shaft in the seafloor. It is an active machine. In 2021, it reminded everyone on the surface. At 19:28:32 UTC on March 4th, near 29.735 degrees south and 177.282 degrees west, the Kermadec Islands region produced a magnitude 8.1 earthquake. The source lay along the same trench system, the same subduction boundary, the same moving architecture that creates hadal depths in the first place. ANOAA DART 4G buoy, station 5401001, about 703.2 kilometers from the epicenter, recorded the tsunami 45 minutes later. New Zealand issued evacuations. Fear runs in both directions here. Almost 10 kilometers below the surface, pressure can turn a specialized vehicle into floating scrap. Above, along the same structure, strain can release as a megathrust earthquake strong enough to move the sea itself. The trench links biology to geology, the invisible deep to the inhabited coast. Kermadec feels different from a simple depth record. The pit is terrifying. The process is worse. A blue hole can trap a diver. A vent field can burn or poison. A trench like this keeps moving while scientists are still trying to map it. Even the animals carry evidence of adaptation. Hadal fish such as Nodulaparis kermadicensis have been studied through otolith growth zones and oxygen isotopes, tiny records locked inside the body, because ordinary observation is so hard this far down. The ecosystem has to be rebuilt from fragments, bones, chemistry, pressure-proof samplers, brief camera passes, and sometimes the last data a doomed machine sent before the line went dead. That brings the giant amphipod back into focus. In most places, An outsized crustacean would be a curiosity. Here it is a clue. Hadal gigantism is not decoration. It points to an environment that is severe, food-limited, and strangely selective, a place where evolution does not make life comfortable, but can make it specialized enough to exploit what little arrives. The Kermadec Trench is deep because plates are still converging. It is dangerous because that convergence still produces earthquakes and tsunamis. And it is biologically unsettling because even the scavengers bear the signature of that pressure-loaded world. So when Nereus disappeared in 2014, it was not only the destruction of a robot, it was the trench refusing inspection at the exact depth where some of its most revealing life begins to appear. Pieces of the vehicle came back, the full scene did not. Below the breakpoint, in cold water under nearly 1,000 atmospheres, the amphipods kept feeding in the dark. Number 3. The Fast Plate. The Fast Plate. On June 10, 2019, the support ship DSSV Pressure Drop held position over a stretch of the Southwest Pacific that looked empty from the surface. Below it was horizon deep in the Tonga Trench, the deepest point in the southern hemisphere. Victor Vescovo climbed into DSV limiting factor and began dropping alone toward a seafloor no human being had ever reached solo. People usually picture a trench as a crack, a gouge, a wound in the seafloor. Tonga suggests something colder. The bottom of the ocean may not be split open at all. It may be being taken. The team had to locate the target before the dive even began. The 5 Deeps expedition did not arrive with one sacred coordinate and descend on faith. They mapped. Multi-beam sonar swept the trench floor in strips and built a shape out of echoes. In a place this narrow and this rugged, the deepest point can shift when the map improves. A few hundred meters one way, and there is a ridge. A few hundred the other, and there is a deeper slot. In the Hadal zone, from 6,000 down toward 11,000 meters, certainty costs work. You do not look down and see the bottom. You infer it from sound returning through miles of black water. The descent was a record attempt. It was also a test of what this place physically does. Tonga's answer is strange. It is not about teeth, venom, or temperature. It is about motion. By the time limiting factor reached about 10,823 meters, confirming horizon deep as the second deepest known point on Earth, the trench had still hidden the main event. The Vescovo reached the depth. The mechanism stayed out of sight. The first hard clue is speed. Continents move slowly enough to feel abstract. Fingernails grow, grass rises. Plate tectonics is supposed to belong to that scale too. Along the Tonga subduction zone, the numbers stop sounding geological and start sounding mechanical. Older estimates put convergence near 15 centimeters a year. GPS-based work in northern Tonga pushed that much higher, up to about 24 centimeters a year, 240 millimeters, often described as the fastest plate velocity recorded on Earth. Nothing snaps in a single instant. The force is steadier than that. A piece of the planet keeps moving in one direction, year after year, with no sign of stopping. That pace means the trench cannot be treated as a static abyss. The Pacific Plate is being forced westward beneath the edge of the Australian plate system. The island arc above is active. Earthquakes cluster through the region. Volcanoes rise in a chain. Behind that arc, the Lau Basin opens as the system stretches and rolls back. The whole setting acts less like a crack in rock and more like a machine under load. One slab descends, another margin retreats. The seafloor is rearranged while the ocean hides it under a flat skin of water. The scale mismatch is hard to shake. You float on the surface of the largest ocean on Earth. Beneath you, a plate of crust is moving faster than most people imagine stone can move at all. No sound reaches you from it. No seam splits the sea where you can see it. The signs arrive in bursts instead. A quake, a chain of volcanoes, a trench deeper than 10,000 meters, a map that keeps changing because the terrain is too extreme to simplify. Tonga feels less like a hole than an exchange. Material goes in, consequences come out. The biology makes the place feel barer, not busier. Trench documentaries train people to expect monsters. In Hadal reality, the deeper image is often bait. Drifting particles, amphipods swarming where food appears, and long stretches that seem almost empty. Specialized snailfish can live astonishingly deep, but vertebrate life does not continue downward forever. pressure narrows the range. At the greatest depths, the scene can look less like an ecosystem in the ordinary sense than a waiting room for whatever falls from above. Life persists, but on terms set by compression, scarcity, and chemistry so severe that large, active predators are no longer the point. The place is. A ship can pass over Tonga and meet only weather. A radio signal can cross above it and never notice. Below, the seafloor is entering Earth. Not metaphorically, not on some distant poetic timescale. Physically, continuously. With enough force to build arcs of fire, and enough patience to redraw the map under every expedition that comes looking for a final answer. Horizon deep is frightening not because it is only dark, or only deep. Here, depth is the visible edge of something larger. That larger act resolves the paradox from the start. A trench is not merely a crack. It is a boundary where oceanic crust bends, sinks, and is carried down into the mantle system through subduction. The Pacific Plate does not end at Tonga. It disappears there, westward, centimeter by centimeter, into heat and pressure no camera can follow. On the surface, pressure drop drifted over quiet water. Far below, the seafloor was already leaving. Number 2. The other Mariana. In February 2012, a deep ocean lander descended into the Mariana Trench system at 12 degrees 3.924 minutes north, 144 degrees 34.868 minutes east. Those coordinates sound precise enough to pin a miracle to a dot. Down here, they mostly mark how hard it is to be sure what, exactly, the instrument reached. The target was Serena Deep, a hadal low point in the same trench system as Challenger Deep. But the significance was not its rank on a list. It was what happened when the lander arrived. Its pressure-calibrated sensor gave a depth of 10,677 meters. The number matters less as a credential than as a condition. At that depth, pressure exceeds 1,000 atmospheres, enough to turn every seal, housing, cable, and lens into a point of possible failure. A reading like 10,677 meters is not just very deep. It means every image is hard-won, every movement slowed, every interpretation filtered through instruments operating at the edge of what they can survive. And when the instrument settled, it did not touch down on a flat basin floor. It came to rest on the trench's inner slope, near exposed rock and talus, debris from a wall that keeps breaking and sliding into deeper darkness. That changes the entire scene. A flat bottom gives you a reference. A slope gives you instability, uneven footing, and the possibility that the point you came for is not a clean point at all, but part of a shifting, fractured system. Sunlight had never reached it. There was no horizon in any ordinary sense. Only the camera's narrow cone and the particulate black beyond it. Then the frame began to turn, slowly, probably pushed by bottom current. Waves, not the dramatic violence people imagine when they picture the deepest ocean. A current, nearly 10.7 kilometers down, rotated the camera inch by inch until it built a rough panorama of the trench wall. The motion was almost courteous. That is what made it unsettling. It meant the water was not still. Even here, where depth suggests silence and finality, the environment was exerting force, enough to move the instrument and quietly alter what it could see. The images refused to stay simple. Instead of showing only mud, collapse, and bare rock, the cameras caught pale, structured deposits on hard surfaces, films or patches organized enough to raise a dangerous possibility. Researchers considered whether these traces might record chemolithoautotrophic microbial activity, life drawing energy not from sunlight, but from reactions between rock and water in one of the darkest places on Earth. But the tension is sharper than life exists in extreme places. The pale structures are not a solved mystery. They may reflect biological communities. They may also be non-living mineral processes arranging matter into forms that only look alive to a camera dropped into a cold, lightless trench. The deposits do not merely suggest discovery, they threaten classification itself. If they are biological, then life is operating on a steep hadal slope under pressures that make even observation difficult, extending the boundary of where active ecosystems can persist. If they are mineral, then something equally troubling follows. Some of our best instruments may be mistaking chemistry for biology at the edge of known life. The deepest ocean, where sampling is rare and direct verification is brutal, a false positive does not stay local. It undermines how we decide what counts as life at all. That is why Serena Deep matters beyond its depth ranking. It is not simply another contender in the Mariana Trench. It is a place where the terrain, the pressure, and the limits of imaging all conspire to produce evidence that may be profound or may be misleading, and may not let us tell the difference. Verification is where the neat story breaks apart. Serena Deep's 2012 landing site came in 55 meters shallower than an earlier depth reported by Fryer and colleagues in 2003. 55 meters is not much if depth is just a headline. Here, it changes confidence. It tells you that deepest can depend on where an instrument actually settled, how the slope was measured, how pressure was converted, and whether the mapped target was a stable bottom or only one fragment of a larger broken descent. The difference is enough to expose the false certainty packed into ranked lists and singular labels. Later exploration reinforced that instability. From April 20th to May 11th, 2016, NOAA ship Okeanos Explorer worked in the Mariana Trench Marine National Monument, established in January 2009. The expedition explored canyon and slope terrain, dropping towards Serena Deep. Not one dramatic bullseye. Terrain, approaches, sidewalls feeding into deeper structure. That matters because a map can make the eye expect a final dot, but the seafloor offers gradients, walls, debris fields, and moving geometry. Point may be less a destination than a temporary reading taken within a complex system that keeps slumping, collecting, and obscuring itself. Even the broader maps are thinner than they look. As of June 2024, only about 26% of Earth's seafloor had been mapped in high resolution. That figure is not trivia. It means most of the planet's bottom remains too coarsely seen for confident detail, and even famous trenches inherit authority from incomplete coverage. A label on a map can imply stability that the actual terrain does not grant. In a place like Serena Deep, where a lander arrives on a slope and a current turns the camera, incomplete mapping is not an abstract gap in knowledge. It is part of why certainty keeps slipping. So the real unease is not that Serena Deep is obscure, or that it may be slightly shallower than Challenger Deep. It is that one of the most extreme places on Earth produced images of pale structures that might be alive, or might be mineral, on a wall too steep and unstable to make certainty easy. The camera turned. The deposits held their shape. And the deepest implication remained unresolved. In the dark, under crushing pressure on a moving slope, our instruments may have seen life, or only the seafloor imitating it so well that we still cannot prove which one was looking back. Number 1. 11,034 meters. Down. Reached bottom. No fish seen. That is what the log said on January 23, 1960, about 200 nautical miles southwest of Guam, when Jacques Piccard and U.S. Navy Lieutenant Don Walsh took the bathyscaphe Trieste down toward Challenger Deep. No poetry, no flourish, just a mechanical sentence at the end of nearly 5 hours of descent into the lowest-known pocket of the Mariana Trench. Above them sat almost 7 miles of Pacific water. Around them, pressure climbed toward more than 8 tons on every square inch of hull. Partway down, they heard a crack. One of the outer plexiglass window panes had fractured. The pressure sphere held, but the warning was clear. At this depth, damage does not stay theoretical. A failed component would not just end a mission. It would erase the crew before they could report what happened. They kept sinking. Inside Trieste, there was no spacious cockpit, no cinematic dome of glass. Just 2 men in a steel sphere suspended beneath a float, dropping through black water that would crush ordinary metal shapes flat. When they finally touched bottom, the seafloor did not appear as a clean finish line. It rose as silt, a pale cloud kicked into darkness by the impact. The deepest known place on Earth answered arrival by blinding them. They stayed only briefly, then released ballast and began the long climb back. Humans had reached the deepest place on Earth. Even that did not settle what, exactly, they had reached. Challenger Deep resists because it breaks measurement, bodies, instruments, and even recovered evidence. The first threat after survival is misreading the bottom itself. For decades, the trench carried a clean, famous figure, 11,034 meters. It sounds fixed. It sounds like the kind of number a crew could trust while planning a descent. But Challenger Deep is not one simple point. It is a broken cluster of basins and depressions, and the only way to estimate that floor across most of its area is to send sound through nearly 11 kilometers of ocean that bends and distorts the signal all the way down. If your correction is wrong, your map is wrong. If your map is wrong, your descent plan is built on a false floor. The deepest place on Earth is hard to reach safely, in part because even its depth does not stay still under measurement. That uncertainty is not academic. Sonar returns do not come back with certainty attached. They come back through water, layered by temperature, salinity, and pressure. And the last meters matter because the bottom is where a sub must stop descending before impact, where a sampler must know what it is touching, where a mission decides whether it has reached the target or the wrong hollow beside it. Modern analyses have narrowed the depth, but not into a single untouchable answer. The point is not that scientists cannot count. The point is that Challenger Deep can turn even precise surveying into a moving risk. That is why later descents did not make the place feel routine. More than half a century passed after Trieste before James Cameron descended solo in Deep Sea Challenger in 2012. Victor Vescovo followed in 2019 and returned repeatedly with better mapping, sampling, and observation. But those revisits did not tame the trench. They exposed how much depends on instruments trying to read a floor that refuses to present itself cleanly. And then the threat shifts again. Even when crews and vehicles reach the bottom, pressure can still destroy the evidence they came to collect. Life exists there, but not in a way the surface can easily receive intact. Researchers working in the Mariana Trench had to develop pressure-retaining samplers because ordinary recovery can alter or collapse the very tissues, chemistry, and microbial systems under study during ascent. A specimen brought home from Hadal depth may no longer fully be the thing it was below. Challenger Deep does not just endanger explorers, it can falsify their proof. That changes how later discoveries feel. They are not tidy additions to a list. They are glimpses snatched before the trench or the ascent distorts them. Amphipods collected from trench environments near the deepest parts of the Mariana system revealed microplastic ingestion. Pollution had reached the one place people once imagined as too remote, too deep, too sealed off to touch. The shock is not only that life survives there, it is that our contamination got there first, and the pressure makes even that evidence hard to recover without changing it. So the chain of danger keeps tightening. A cracked pane warns that the descent itself can fail. Uncertain depth means the map guiding that descent may be wrong at the point where error matters most. Extreme pressure then threatens the samples and organisms that might explain what lives below. By the time we do retrieve evidence, we may find that the deepest place on Earth is not pristine waiting, but an environment already altered by us. That old log line lands differently because of all of that. No fish seen. Brief, careful, understandable. Trieste touched down, stirred silt, and left. The crew did not arrive at a clear, illuminated bottom ready to give up its meaning. They arrived in a place where impact blinded the view, pressure had already announced itself with a crack, and the environment itself interfered with observation. The deepest place in the ocean is not just deep, it is a place where the route down can break, the floor can be misread, and the evidence can change on the way back up. Which means the next descent faces more than darkness and pressure. It may reach the bottom and still not know exactly where it is, what it disturbed, or how much of what it brings home has already been altered before anyone can understand it.